Hello everyone, I'm Alex. I'm here to talk about how one would use MLIR from languages that are not C++. It's not that we hate C++, but there are other languages, or so I've been told, and people sometimes want to use them. And we thought about those in MLIR, and we decided to build first a C API with also some better promise of stability than what the C++ API gives you, and then we exercised this API building Python bindings, because apparently all of ML is being written in Python, and we're all being paid by ML these days. So it sounded like a good thing to do. So I'm here to present this. This is more like it's a tutorial, more of a lecture. I guess I failed my calling as a teacher and became an engineer instead. So there's a lot of code and text on slides, but that's what a tutorial is. Don't hesitate. If you have questions in the middle, there are mics. They might be on. If they're not on, just wave at me and we'll wait for them to be on. And if you have questions in the middle, you can ask in the middle, you can ask in the end. And yeah, there's a lot of API calls and stuff. You might ask me a question, how do I do X? And I might not be able to give you the correct answer out of my brain, because it's an API with 1,000 of calls or something. But I'm sure I can point you to the right direction. Okay, let's get started. The short agenda of this, we are going to talk about API, like design of the specific API we have, and the basics of how it works. We are going to look at how do you traverse IR that already exists. We are going to look at how you would create IR objects, such as operations, attributes, and types. We'll see how the heck you're going to build this thing, because build systems are hard. And finally, we are going to see how you would actually want to transform that IR by running a pass or writing a new pass. And we are going to do this in C to start with, and then rinse and repeat and do exactly the same order in Python. And to start, I put the fancy title of C API design goals, but basically there are very simple design goals. C API is like C is a language that almost any other language can interoperate with. So having a C API is something that just comes naturally. We want to have one single interface, and we MLIR developers, primarily writing C++, also kind of know C, and we can understand if there's a problem with C code, and well, I cannot understand if there's a problem with your Haskell code or Julia code or whatever other language. So it's a single point of interface that we can all understand and fix, and other bindings are possible on top of this C interface. There is something that I put as a weak stability guarantee. MLIR, like the rest of LLVM, does not have any API stability guarantee whatsoever. We try to be conscious about breakage in C API. So whenever possible, we are not going to break C API. And then C makes it easier because there's no function overloading, no classes, no inheritance, just names. So whenever possible, it tries to be stable, and we actively push back against let's just add an argument to this function. If you want, add another function with X or extended or a config or something. But it's not a guarantee. It's not tied to versions, but it's pretty stable. I had some projects written 3 years ago, and they didn't think I would have to change them, and I didn't. And the other, it's not a goal, it's more a side effect of the other goals. It's biasing towards simplicity and being minimal and minimally usable. I do not actually expect people to write code using MLIR, using C. If they want to, they're better off writing their own API shim around these APIs to actually use it in a more C-like way. So one boring thing to start with, but it's actually useful when you want to discover, is naming conventions. And well, it's MLIR, so everything is prefixed with MLIR. It's just MLIR, not LLVM MLIR, nothing, just MLIR. Types are capitalized, so if you see something starts with a capital M, MLIR operation, MLIR attribute, it's a type. If it's not capitalized, it's a function, and there's nothing else in C++. Well, there's variables, and variables, you name them whatever you want them. And there is a bigger part of naming convention when we use that convention to communicate additional semantics about what the function does, in particular about the method functions and some information about ownership. So if you have a function that in C++ would have been a class member function or a method in Java, that function will have a name that starts with the object that it operates on. So MLIR operation create, it creates an operation. MLIR operation get operand. Its first argument will always be an operation. So it's a function that relates to an operation. Some of them also have action words that are meaningful. So for example, something that says create in the name, it will create a new object and give ownership to the caller. It means that the caller is in charge of then freeing this object by calling a function that has destroy in this name. Typically, you would have MLIR operation create, MLIR operation destroy. And as I said, if you have other flavors of this, you'll have MLIR create function by parsing, or MLIR function parse create, something like that. And it will always have the create, and creates is a signifier that this actually allocates and gives the allocated object to you, and it's your burden to deallocate that, and because it's C, it's really important that you actually do that. When something is owned by another object that you do not have to deallocate, it will have a get suffix. So when we have types and attributes and other context-owned objects in MLIR, you will typically have an MLIR attribute get, like here. It will actually allocate sometimes an attribute in the context. But because it's the context that owns it, and it's the context that will have to deallocate it, it's called get. You get it, you use it, you don't have to do anything else with it. Then let's move to the type model. And we were trying to be kind of simplistic with it. And then C does not really have a very developed type system, so we kind of stayed with the same minimalistic approach. So we only expose top-level objects in MLIR. You know, MLIR is extensible, and I forget to mention, but I assume whoever listens to this kind of knows what MLIR is more or less and how it's structured. If you don't, well, ask me a question, but it's not an MLIR beginner tutorial. So we have these top-level objects, operations, attribute types, some others. And we only expose those. We do not expose any of the subclasses. So if you have an integer type or a float type, or if you have a function operation or an add operation, you will not find an equivalent of that directly in C. They will all always use a superclass. So if you have an add operation, it will be MLIR operation. If you have an integer type, it will be MLIR type. In function names, in naming convention, you will see that. So you might see an MLIR float type get bitwidths, or MLIR float type get floating point semantics. That is an indication to you, the user of the API, that this function, while it does take an object of MLIR type as a first argument, it actually expects it to be a specific subclass in C++ sense. And if you give it something else, it will just assert. So that expectation is encoded in the naming convention, and it's up to the caller to verify if they're not sure that their type is, or their operation is of the right type. So none of these inheritance trees are materialized, and all of these things are essentially type constructs. So inside there will be a pointer, and the operation is already a pointer. Attributes and types are actually pointers hidden inside the C++ class. So it will be just that pointer, and it's cheap to pass around. You should never ever have a pointer to MLIR attribute unless it's a list or any of these objects. And since all of these are nullable, all of these objects might be null. They're pointers. So before you use something, you might need to check if you're not sure of the provenance, if it is null or not, because if it's null and you just pass it, it will again assert. Like I said, minimalism, and well, it's C is sharp, it's dangerous, lots of undefined behavior, so let's embrace it. Okay, so with that knowledge, we can try to look at how one would traverse a piece of IR that somebody else created. That's the first basic task you would do with any MLIR-based tool. And as a reminder, MLIR has this recursive structure where it starts with a top-level operation, such as a module, and that operation has regions attached, and each region is a list of blocks, and each block is a list of operations, and each operation has regions, and so on and so forth. It's recursive. So when we want to traverse that, well, we start with an operation. We want to look inside. We may want to look inside the regions. First, we need to know, are there any regions? And for that, we can just ask the API how many regions are there. And then we can get a region based on its position. Here you can see int ptrt. At some point, we made the decision that, we're in 2024 right now. Let's assume at least C99. So we use int pointer t, we use bools, we use at least C99. We don't go beyond that, and we might want to assume C11 soon, because let's be honest, it's a very old standard. And that's just the basic thing that we have. We can get a region. Same way we can, almost the same way we can get a block in the region. Here it gets a bit more interesting because, blocks in a region and operations in a block are actually linked lists of blocks and operations respectively. So you can get the first region, or the first block, in a region, and then given a block, you can get the next block in the same region. And going back to the naming convention, because it's kind of important here, because the second function operates on a block, it's called MLIR block get next in region and not MLIR region get something, because it doesn't even take a region. And that's kind of an easy mnemonic to remember how to, you open your editor, have autocomplete working, you type MLIR block, and you have an autocomplete of all the things you can do with blocks. And we have the same with operation, so it tries to be consistent. So get first block, get first operation, get next in region, get next in block. It gives you next in block. And keep in mind, it's a linked list. We could have exposed an API where it gives you an ends operation in the block, but it's we actually did that in Python, but it's kind of expensive. So we decided not to expose it and just throw this at you saying, this is a linked list. You should know it's expensive. It's expensive operation. If you're writing C, you might care about performance, I think. Okay, let's look at a simple example. As usual with MLIR, we start by creating a context. Or if you're given an object that has been created already, it will have a context, and you will have MLIR operation get context to extract it from there. And here I put some example where I parse it. I didn't put the IR I actually parse. I'm just going to assume it's a module with functions in it. And it creates, as you can see, it says MLIR operation create. So it means it creates a new operation, and it returns this operation to you, and you're in charge of destroying it. It takes the context. Everything in MLIR wants the context. It takes the string representation of the IR. It also takes the file name. File name is not always reasonable, but that's just how the C++ parser is structured. It assumes you're kind of parsing from a file. If you don't just put a minus saying it's only there for diagnostics. So whenever it prints, it says in file this, on line that, the problem was this. If you put std and minus, doesn't care. What else you see here is this MLIR string ref create from cstring. And there are a bunch of functions that handle this LLVM auxiliary data structures like string refs. And if you worked with C, C has strings. There was a paper saying, the C string being designed the way it's designed with a null terminator is $1 billion mistake in the industry. And it's super expensive. You do strlen, and it's linear in the length of string. And string ref wants to fix that by saying, how about we store the pointer and the size? So here's converting one from another. So you have to create string refs. You can almost never pass a const char. You almost always need string ref, and it's also not owning. So when you see a string ref, same as in C++, it's a reference to a string. So when you see a string ref, you do not own it. You do not pass ownership. If you create it from a C string from a literal here, it will just have the pointer literal and the size, and it will do the strlen under the hood. If you create it from a C++ string, it will just point to the same data. So string ref, same as C++, obviously it's not owning. Okay, and then let's say we have this module, that's module based on operation. We get the first region, call it a body, using the get first region function. We can similarly get the first block of that region. And let's say I want to do something about public functions, I just want to list public functions or public objects in this module. So for that, I will create two string refs. Again, both are not owned. And one is calling MLIR symbol table get visibility attribute name. That's a mouthful. But the way to deconstruct it, MLIR is, it's a namespace, it's MLIR. Symbol table in this case is the name of the class. In C++, you have symbol table class. That's how you operate with, guess what, symbol tables. And it has an attribute name that all symbols should have. We don't know what it is. Well, I know it's sim_name, but I don't want to hardcode it. And then I want visibility to be public. So I create the second string saying, well, I'm going to look for something that has public visibility. And to look for it, I'm just going to go and iterate over all the operations we have. It's a list. You can write a simple for loop, going from the first operation to the next. And inside, you can go and query, hey, operation, give me the attribute with the name contained in this visibility. So what's the visibility of this? And it's an attribute. It's an object. I want the value, so I can get MLIR string attribute get value. And here's another example where MLIR attribute itself is a top-level class. We only use that. And I do MLIR string attribute get value, which says this function expects a string attribute. What did I forget here? Well, I forgot to actually check that the attribute returned is a string attribute. I kind of assume the IR is valid and the verifier has ran. And because the verifier verified that if the attribute exists, it's a string attribute, I don't have to do it myself here. And basically, normally you would have to check before you do so. And then it just string references, so we can do a simple comparison and say, if they're equal, then we have found the function has public visibility, and we can do something, for example, print its name. This is a very minimalistic example of basically anything that you would want to write with IR traversal will look like this. It's a lot of boilerplate, it's verbose, but it's kind of simple. Like it's something you wake me up in the middle of the night and ask me to write it. I don't even have to wake up, I'll just go and write it. Okay, we know how to traverse IR. How about doing something more useful and creating it? I briefly touched on the ownership model before. Let's make it more explicit. So there is an ownership model that's we kind of derived from how the MLIR, IR, and C++ operates. And well, by default, we say there is no ownership transfer unless specified otherwise. And the ways to specify it is encoded in the naming convention. So as I said before, if there is create, it means the caller will own the object that's returned. If the function contains the keyword or the word take, it means that the function will take ownership from the caller and transfer it to the callee. And then the callee will take care of it. It does not specify how exactly it might associate it with the container, put it in IR structure, but you are no longer in charge of the object's lifetime. And yeah, there is MLIR something owned type that expects the thing to be passed into it to be owned by the caller. And then finally, there is the get that returns thing, typically context owned, basically returns the thing that does not do ownership transfer. And that's pretty much all there is. So MLIR itself, you have an operation, it owns the regions own blocks. So as a user, you only own the top level operation and the context. So again, a simple example starts by creating a context. You own the context. You see it because you call the create. And then to create an operation, you first create yet another auxiliary object that's called operation state. And operation state is basically a struct containing everything there is to know about an operation before creating the operation. In particular, it contains the operation name. Here, it's a built-in module. And the location, here the location is unknown. Please don't do that. I just wanted something short and slides that please use correct locations when you can. There's like file line colon location. There's a fuse location. There's a string location. There's plenty of those. You can combine. You can even add your own. I just wanted a short slide. And then, you are about to create an operation with a region because, modules have regions. So how about you create a region while you go and say MLIR region create. That creates a new region. For now, it's detached. You, the caller, own it. And for a module, it's kind of enough, but there are more things in the state. But for now, we'll just say it's a module at an unknown location, has one region. The region is created, it's empty. And what we do here is we add an owned region to the state. And this does the ownership transfer. It says the caller owns the region and it gives the transfer gives the ownership of this transfer to the callee. And as many of these things, it takes actually a list, so we have to create an array out of nowhere and just pass the size of this array and the list of regions to it. This thing transferred ownership, there is nothing else we can do about it. And then when we're done with this state, we can do MLIR operation create, and that will actually create an operation finally after all these things. And now this operation object owns the region that you just created, and you own the operation. And then when you're done with this, don't forget that you need to destroy the objects you created, because C memory, you need to avoid leaks. So creating operations is rather straightforward. If you had written MLIR C++ before, you have seen the operation state class. It's the same, but exposed in C, where you need to add operands, results, attributes, regions, properties, successors. That's all there is. And they all kind of have a similar API, so it takes a pointer to the state. State is this helper class, so you can pass it, you have to pass it by pointer here. And it usually takes a list of things, and the list of things systematically in all of C API, we are trying to be very consistent. It's a size as int pointer type, and a pointer to a flat list of the things you're passing in. And what's good about operations is it works out of the box for any dialect. You don't have to do anything about it. You know, you have your own dialect, like custom Alex dialect, dot custom Alex op. All you need to change is pass the name of the function. And then you have to just give the list of operands in the same way the operation expects them, same with result types, same with regions. Basically, you can do it immediately for any dialect, including the dialects that do not exist. If your context allows unregistered dialects, you can create operations from a dialect that does not exist and happily run with them. The problem with that is it does not do anything else. It merely creates an operation. It does not run the build function, basically the constructor of the operation that might be, I don't know, inferring result types or taking a string and creating a string attribute out of it. You have to do all of that yourself, and it's kind of annoying. And if somebody I have ideas, but if somebody else has ideas how to fix that, they're most welcome. And most importantly, it does not verify. So it creates an operation, and the operation just exists. If you want to check that the operation that was created is valid by the verifier condition, you actually need to run the verifier on that operation. That is intentional because sometimes you want to create operations that are not valid when you create them, and then amend them so that they become valid. So verification is separated in C API as it is in C++. For types, and I'm going to refer to types and attributes interchangeably because they're really, really the same thing underneath. We are not so lucky. There is no generic format for types. We cannot just pass a string for it's an integer type. We actually need to do more work, and we need to define additional functions. So for all the built-in types, and many of the upstream dialect types, we already have C API, so I just took one of them. I happened to have the transform dialect open in a tab, so I took that, but basically it works for any other thing. So for that, you need to define functions, and you need to define what it's called, the registration of the dialect if it's the first time the dialect is exposed. So let's look at that. If you want to bind, like if you want to provide C API for your dialect, that's how you do it. So you know it's C, so you write a header, you write a C file, and you compile, and you're good. And since it's all by default compiled in C++ mode, just put your ifdef C++, extern C, and then the first thing you do is you declare this dialect registration. This is a macro that will provide hooks for registering dialects with the MLIR context. If you worked with C++, you know that you have to register things before you use them. Same here. We'll have an example later on. And then in the source file, there is a counterpart where in the declaration in the header file, you have a declare dialect registration. There you have a define a dialect registration. It takes the name of the dialect, the unstringized prefix of the dialect in C++. That's basically, look that up in the documentation. It's pretty stable. And then after that is done for the dialect, you can move on to defining functions, because it's C, there's only functions for the types you have. And there are two things that are mandatory, and the third thing that makes it anyhow useful. So the two things that are mandatory are the is a something function, and here it's MLIR type is a transform operation type. And the second one is MLIR transform operation or MLIR type name get type ID. This must be defined for any type you expose because we have auto-generated code that relies on this to do type checking and to dispatch based on type. So type IDs are important, and it's the thing that identifies type in the MLIR context, and then just checking that an MLIR type object is of a specific subclass. It's a pretty fundamental thing you want to do. And then type get creates a type. So that's what makes it somewhat useful because we can actually create instances of this type and use it somewhere. And then one important thing, on the left part is this MLIR C API exported. That's, if you worked on Windows, it's decal spec DLL export, but it's basically what makes it visible in a library, and then when we disable everything, this is still visible. Implementation of that is really straightforward. To just delegate to the C++ code. So is a something, well, we call LLVM is a something. Get type ID, you call get type ID. And get something, you just call type name get, like you would normally do in C++ code. And what's interesting here is we have these additional functions called wrap and unwrap. And we define them for all the upstream, like relevant upstream objects. And these let you go from C to C++ and back. So if you have an MLIR : type from C++, you can wrap it and you get an MLIR type from C. You can unwrap it and get to MLIR : type back. And that's how basically, that's one word you put there and you call a C++ function. That's all you need to do in C API. And then if you have something more interesting, you can define more functions. You can define, for example, a function that gets a parameter of the type for a parameterized type. Then you need to link this in for C. It's not hard. We have CMake macros to create a public C API library. I just wanted to put on the slide because if you look upstream, it says add MLIR upstream public C library that you shouldn't use in the downstream, but some people try and it doesn't work for them. But it's just basic CMake. We can do the same with interfaces and basically any other IR object. I just highlighted interfaces because interfaces, are subclasses of operations and types usually. And for this, again, we need type ID because interfaces have type ID. And we can have a check instead of saving is some interface. We have like implements interface because it just reads better. But that's pretty much it. And for regular interfaces, we can take an object, the interface of which we are implementing. And for static interfaces, we take an identifier that lets us understand what class it is. So for operations, it would be a string with a name, and for attributes and types, it would be type ID. And that's pretty much it. Now let's do something more useful with it. So let's try to mutate this in a pass pipeline. So, if you know how to run a pass pipeline, it's kind of the same. So you create a pass manager. Again, it's pretty consistent. So you have a pass manager, you create a pass manager on a specific operation. There is this weirdness in MLIR between a pass manager and op pass manager. I'll spare you that, but basically sometimes it expects one, sometimes another. There's a way to go from one to another. And then you can, for example, parse the pass pipeline. Here I'm doing canonicals and CSE. And just if it's a failure in parsing, you will do it. And somebody might, I sort of expect a question here, but how about registration? Because, if you haven't registered your pass, you cannot use it in a textual pipeline. And that's where we have these, for example, we have these functions, MLIR register, transform something and something. But most importantly is these things are defined in TableGen. So we define pass names and descriptions in TableGen. And we have to generate these before we can use them in a pass. So in addition to generating the C++ includes with pass declarations, we also have to generate the C includes and implementations for those registrations and actually call them before creating the context so it's known and obviously before running the pass pipeline. Okay, you can create external passes. I don't actually have time to explain how that works, but it's basically a C++ structure that looks very similar to how you would write a pass in C++, but in C with function pointers instead of virtual functions. That's it. Okay, now that you're all overloaded with C, let's look how to do exactly the same from Python. Sorry for being repetitive, but actually, having learned that about C, you'll see how much Python is nicer and all the effort you'd have to do if you have to write your Python bindings from C. And if you do write your Python bindings, they're likely being based on the C API. So let's go back to the whiteboard and see what the design is. And the main design point we wanted to have is, how people use Python. They want to just go say pip install MLIR, open their editor or their Colab or whatever it is they're using, and type import MLIR and expect things to work. And try to be as Python friendly and Pythonic as possible. So yeah, just do import MLIR, and downstreams might want to re-export it. So Erie has its own thing, so it has Erie.ir instead of MLIR, if I'm not mistaken. I'm looking at Erie people here. Yes, so that's exactly the model we wanted to follow. It's built on C API. We wanted it to be generic, but to be honest, the real reason was F exceptions. When you have PyBind, it wants exceptions, and LLVM builds without exceptions. And well, C does not have exceptions, so it's not a problem. So going through C kind of removes that problem, and in addition removes all the nasty ABI problems. I've been told C++ does not have a stable ABI. C kind of does, so helpful, but yeah, it was really exceptions. And well, now people build other bindings, and it's kind of nice. It's okay to use some header-only C++, and we use PyBind 11, or put like nanobind anyone is just a volunteer to port this to nanobind, because that's like 10 times more performance than PyBind. Please do. And all the explicit registration things are still visible in Python, because if you read the Python, whatever they call the PEP 8, it says one of the points is explicit better than implicit. We adopted that for registration. One big thing I put it on this title slide is we tried really hard, many people smarter than I am, tried to make it work with multiple .so libraries from multiple projects. It has never worked. So don't waste time, just link everything in one big library loaded from Python. I know it said, if you can solve it, please, by all means, please solve it for us, but we haven't managed so far. And it's been like 4 years probably to find a way to have like a separate libMLIR, a separate libMLIR dialect, separate libErie dialect, separate libmodular dialects, and have that all work together in Python. We can discuss a specific problem after the talk. It's not a problem of the tutorial. So please, please, please don't try multiple libraries. It will fail, it will hurt. It might work the first time, the second time it will fail the third time. Okay, traversing the IR, we've seen how to do it in C. Look in Python, well, Python is much better in conciseness. So as a reminder, again, it's this recursive structure with operations, regions, blocks, and it's reflected in Python, except that because we can be more flexible, we now have an IR operation that has regions. Regions are exposed as regions property. It's iterable. You can put it in a loop. You can have it in a generator expression. You can convert it into a list. Anything you can do is normal iterable in Python. Same for blocks, same for operations. Blocks and operations are actually indexable with an integer, but as you remember, it goes to C, and in C it will go a linear traversal every time. So when you do blocks and iterable, it will be actually good. It will just take next. But if you just take the fourth element and the fifth element separately, it will retraverse the linked list every time. But well, it's Python. Who cares about performance in Python? So yeah, these are iterables. I saw that. And attributes are a dictionary. Well, it's like a dictionary. It implements the protocol. So you can access attributes by name. You can access attributes by a symbol that's like not a string. But otherwise, it's pretty much as if you have written it from scratch using Python data structures. We dropped the MLIR prefix in Python. Don't tell me I'm inconsistent. It just made more sense in Python. Whenever possible, we use properties instead of functions. Basically, the condition is if it cannot fail. Like if this property never asserts, it will be a property, otherwise it's a function, so it can return an object, and it might return none. We try to use container-like objects, so iterables, dictionaries, sometimes actual containers like tuples, and objects that are nullable in C are optional in Python typing sense, so it might be none, and you might sometimes get a none, so when you try to get an attribute by name and there is no such attribute, you might get an none instead, so it's not an assert. And in other cases, we cannot intercept C asserts, but in many places, we are actually adding Python asserts on top, so you can catch those or like handle it in the Python way. And then Python has this packaging structure, so we package the core components, so like the core IR data structures in MLIR.IR package, and then each dialect goes into a sub-package inside dialect, so we have MLIR dialects.lineage, MLIR dialects.arrays, and so on, and basically reflecting the top-level structure of the MLIR tree. Again, all of those might be linked to the same big dynamic library. It's irrelevant to the Python structuring. Okay, let's look at a simple example of IR traversal. We start with creating context. And here you might say, what the heck is that? And that is a Python context manager. This is a thing that kind of ensures you have a lifetime that's not function, because otherwise variables in Python have function lifetime. And it creates a new context, calls it CTX, and everything inside that with statement will operate on that context. It will be destroyed at the end. And inside that, well, you can go and parse a module. And how do you parse a module? Yeah, ir.module, it's where the module lives, .parse. In Python, we decided to expose module. I don't remember why. It should have been an operation, but we have a module, we're stuck with it. In C, we do not have a separate module as far as I know. But okay, there's a module parse. And then we can traverse it by saying, give me the first region, give me the first block. And for each operation in that block, let's get the visibility attribute. Let's check if it's not none, because if it's none, there's no visibility, and let's assume it's private, so I'll just continue. And if the visibility attribute has a value that's string public, well, you can do something. In my case, I just wanted to print all the public functions, for example. So that is very similar to what we had. It's more concise because it's Python, but in other sense, it just basically iterates through the IR structure in the way it's structured. One thing that I put here, yes, question.
Alex, one question about lifetimes, create, destroy. I
Yeah.
think on the C side, you showed that there were, it wasn't only the context that had its destroy function. It was also, I think, like operation and something else, right? First question, for C, do we actually have to call destroy on these things that belong to a module, or is it enough to call destroy on the whole context?
You should destroy the object you own. So typically you would destroy the module that will recursively destroy everything it contains, and then you destroy the context.
What if I destroy only the context?
You leak the operation.
Okay. And here with Python, you have the with statement for the context, right?
Yes. So
what is gonna be destroyed at the end?
So in the end, Python is garbage collected. So here, the with, when you exit the with statement, will actually go and destroy the context. But
after that, the GC will clean up the rest, right?
It may or may, when it comes, it will, but you don't know when it comes.
Okay.
So basically, you should not leak any, that's actually a good point, you should not leak any context-owned objects outside of this with, because you can, in Python, you can assign and access it, and it might crash because you're accessing outside of the lifetime. It might work because you put a safety mechanism in place that we want to remove. I'll get to that. And module is garbage collected. So here it is parsed, it will create a module, and then when it goes out of scope, function scope in this case, eventually it will be garbage collected. Yeah, great question, thank you. And yeah, don't hesitate to ask questions. And what's good about this context management thing is we don't have to pass the context explicitly. We actually designed the API to have a separate magic level. We take a defaulting object that defaults to none, and when there's none, it goes and takes whatever is the context in the current stack of context we create. But basically, what I'm saying here is inside this with expression, you don't ever need to pass the context explicitly. And same for locations later on. So how we looked at how do we traverse IR, how do we create the IR that we want to traverse. And it's kind of the main use case of Python. I think it was on the slide, I'm not sure I mentioned that, but the basic objective of Python bindings is to traverse IR and to create IR. It is specifically not designed to mutate IR. We are not trying to write passes in Python. We could, it's really painful right now, but it was not designed for it. And then creating IR is like kind of, okay, I have my JAX or PyTorch, and I want to go to MLIR, it's written in Python, so it kind of makes sense to connect through Python. Okay, ownership model, getting right to that. So there are objects that are, that's why we have module. So context and modules are owned by the code, so they're owned by Python. They're known to Python, they are managed by Python. And then there's a notion of a detached operation. If you just create an operation and do not insert it anywhere, then it's detached, it's also owned and managed by Python. It will be destroyed when the corresponding or the last reference to it is going out of scope. And then there are these keep alive rules. And I don't fully remember them all, so I had to look them up. But okay, if you have an object that's owned by the context, apparently from my lookup, and contradicting what I said before, sorry, it is going to keep the context alive. So it has a back reference to the context object. And then if you do leak a reference outside of this to something, the context will keep alive, so Python doesn't crash. There was a discussion, by the way, to remove that, so it might work this way right now, but please don't rely on it. Don't do anything outside of context. Basically, your main function in Python should be with context, call something else, and then just assume context is there. And then operations keep alive their ancestors. So if you have a reference to something deep, deep, deep in a tree, you don't actually need to keep the reference to the top level module. We can get to that, and you'll keep the entire tree connected alive by holding one reference to any operation or any, well, actually any operation, not region, not block. Regions or blocks are just pointers, they're not owned in Python. Okay, an important warning here. If you call something, a function call that erases an operation in C++, calls.erase, it is invisible to Python. Python will consider this operation live. And when you try to access that, the good scenario, it will just crash because you access the memory that was freed. The bad scenario is it was reallocated, same address, to a different operation, and you wouldn't know. And I spent months of my life debugging those. So that's really important to not call any code that erases stuff unless it's in a past or another isolated way. Okay, so let's look at a simple example. Again, we start with the context. I don't need the context object, just with IR context. And I also do location because I want to create operations at a given location. I create a module. Well, that module is at unknown location. It has two defaulted arguments that are location and context that we just take from these context managers, but you could, in theory, pass them. And then I create yet another context manager called insertion point. And insertion point will let me insert operations into a specific location, much like in C++ we have a builder insertion point. Except that here is a context manager. It means anything you create inside will go to that insert location. And then if you want to create an operation, well, you do IR operation create. Same as we saw in C, you give it the name, you give it the number of regions, you give it the attributes are dictionary, regular Python. Except that we're not in C, and that kind of looks ugly. And in Python, we went the other way around and said, how about we actually have classes for every operation? So here I'm creating a function, so I have a function package and a func_op in it, and has a constructor. And this is a proper constructor that replaces the ugly IR operation create, and dialects provide custom constructors when they need to. How do they do so? Well, they do so by defining a class in Python in a special place you can see on the slide. And it has an init function. So it's a Python constructor that will take whatever arguments you want, does whatever it wants with it, as long as it forwards them to the auto-generated constructor. Here, question, what is the auto-generated constructor? Well, we are actually generating all of these classes from ODS, so from TableGen, by using this command. And we import code binding functionality. So when you define your own class, you're actually overriding the default class that exists. You inherit from that, and this magic syntax says, well, now the funcop class is this new class, but rename my old class to something else. It's Python, you can do crazy things. This was done by Max. Thanks, Max, but it's also crazy. It works. You tried it, works very well. And you define constructor. It must pass the location and insertion point that may be none, and means take the default, and then delegate to the constructor. So what's auto-generated is that, plus some other things. So you have properties, you might have other functions inferred from ODS, or in your overriding class, you can add more. So if you want to add a property that is not a property in ODS sense, you can. It's a Python class, you can add whatever you want there. So in custom builders, because you have to call that in the end, really stupidly follow the argument list in ODS. So it's on the left and on the right, these are the same. The only question is, how do you map types? So yes?
Can I ask a quick question?
Yeah.
On the previous slide, there was this replace equals true, and I was always wondering what it does, and I tried to leave it away, and then it seems like it still works.
Maybe.
Okay.
I don't have an answer to that, sorry.
Mm-hmm.
So yeah, same order of things, how does it do about types? So it uses a mechanism called, well, I'm not sure it has a name, but it uses a map that maps from the name you use in TableGen, ODS, to the constructor function in Python. So every time you use something in TableGen on the right, so you have symbol name attribute, when you pass something in, it will go look up a constructor in a map called attrbuilder and pass whatever operands you pass to it into that. And that happens on constructor calls, it happens on function calls, basically everything that's generated will have this automatic mapping using that function. And since it is actually a dictionary somewhere inside MLIR Python bindings, you can go and change it, or you can go and edit for your custom types. Okay, I spoke too fast. So bindings for, if you want to edit for custom types, you need to define, again, with operations, it's automatic. With types, it's not. But we have more operations than types, so we suffer through types. Again, improvements are most welcome, but basically what you need to do is provide bindings for the type in Python by calling the C API that you have likely written before for the same type. And you do so by using this thing called MLIR type subclass. It's a slightly creative use of PyBind. If you read the docs, there is a long explanation of why. And if you go and find history on the PyBind repos, there's a long discussion with Stella trying to convince PyBind to do things we think is right. I'm not sure we succeeded, but we use it, it works. So what you do here is you define a subclass of, for example, operation type. You have to give it two things. First, is a function and the type ID function that I said were mandatory in C, and now you know why, so Python works. And then you can define a get method that creates an instance of this type or attribute, and you can define all the other methods. It's basically how you would go around defining a class in PyBind normally. So yes, it requires type ID. Casters are supported. Yes, that's an important point, I think. You can, inside PyBind, we provided enough automatic magic casting that if you just pass a C API instance, it will just work. So it will do the conversion from the Python equivalent to the C API equivalent under the hood. So this needs to go into CMake. Again, pretty vanilla CMake. We have this declare MLIR Python extension macro that we can use, and it's just CMake. Yes?
Another quick question. I was wondering, can these bindings for types and attributes be auto-generated, like same we do for the operations?
Maybe. I suppose they could if there are ODS defined, but we do not have a facility for that.
Mm-hmm, so just not implemented.
Okay. And I am almost at my time. So like I said, the class hierarchy is present in Python, unlike C. And for operations, you need to be explicit when you go from the generic operation by saying .opview to get a concrete class. And you need to say .operation to get back to the generic class. They're all inheriting from something, but the wording here is instance will not work for operations unless you do opview. It's a big gotcha for me. I still get caught by this. But that's basically how you do it. And as I said, we do not want to have IR mutated from Python. You could. So we are, well, I also don't have time. So I'm not going to show you how you mutate IR from Python. You can run passes. You can construct the pass pipeline the way you would normally construct a pass pipeline from a string. I have a facepalm emoji because, why is it a string? And maybe we can fix it. Ideas welcome, but basically, I know it's perfect that I'm slightly out of time here because, don't mutate IR from Python. Just don't. Thank you.
Thank you, Alex, as usual. Really awesome. We have 5 more minutes, really, for more questions.
Yeah.
So, and why you don't want us to mutate IR from Python?
Ownership. Basically, this entire story of Python owning some things and cleaning it up automatically means that if you modify them in C++, Python doesn't know about it, and we do not have a way to tell Python that something was erased or modified or created. It leaks all the ways.
So it's just hard to remove something from Python. You can create it and you can see, but
yes,
you cannot delete.
You can, and basically mutating IR in MLIR typically requires erasing the old operation, creating a new one slightly differently. We do not really mutate in place.
I have another question.
Yeah.
In a C binding, there was take and owned operation. What's the difference again?
There's take is you take the ownership, like you the caller take the ownership from the callee, and pass owned is the other way around.
I see. So take is like owned version of get.
Yeah.
So you kind of discussed a bit about how the naming conventions for the C APIs, and I was curious about the naming convention we should kind of use for in C and both in the Python for kind of overloads, since you can't do overloads in them. So if you have a getter, let's say on many different builders for some attributes or type, what's the recommendation there for how you name those getters?
Well, in C, you don't have a solution. You just come up with names. I hope you just not get 1, get 2, or get overload 1, get overload 2. In Python, you actually have sort of overload with type-based dispatch.
Oh, true, yes.
So we usually do that when we can, and we are pretty bad at it. And there was a long discussion how you name operands for that. But we do Python overload that dispatches based on argument types.
I see, got it. Thanks.
Any more questions? Do you want to see more slides? I have more slides. I won't do that.
We have 2 more minutes for more questions, please. Or Alex can
I'm also
show
happy
the
to breathe if there are no questions.
Yeah. Maybe you can show some of the slides. Oh, yeah. Okay.
Sorry, this isn't much of a question, but is there a boilerplate version of how to hook all of the Python stuff up with an MLIR dialect at one of your links?
It's a good
toy version?
It would have been a good thing to have.
Yeah,
I'm afraid we do not have one. So if you are going to do a new dialect, think about contributing it.
Okay.
Otherwise, the best thing I can do, go find a small dialect upstream that exposes 5 operations and just copy that.
Okay.
Any more questions? We have 1 more minute. Anybody?
You guys are more efficient than I am. Okay, let's
If not,
wrap up.
let's thank Alex once again. Really awesome. Yeah.